Yeah, last section of the year. We'll start reviewing tomorrow in earnest every day during class. So remember, tomorrow BC01 is due. It's due in class. Okay, ready? Everyone? Everyone? Tomorrow. Oh, Friday. What did I say? No, 01. You've already done 01. We're going to go over in class. So if you haven't done it yet, we're going to go over in class tomorrow. So have it done by tomorrow. But hopefully you already have it done.
When are we going over BC2?
BC2, we'll go over that on Friday. Yeah, so BC01, we're going to go over tomorrow. So I assigned it on Monday, but we're going to go over tomorrow. Tomorrow's Thursday, and then we'll go over BC2 on Friday. Okay, so very quickly here, an introduction to the last section. It's called Lagrange error bound, sometimes called Taylor's remainder theorem, all right? And what it does is it tells you if you use a polynomial approximation for some function, how close is that approximation to the actual value, right? So if we wanted to approximate something like, let's say, sine of 1, we didn't have a calculator, how could we approximate sine of 1? We've learned several methods this year for approximating functions. Do what? You can do linearization, right? Linearization we call tangent line approximation, right? And really, remember, now we know that that's really the same thing as a first-degree Taylor polynomial. We could eyeball it on the graph, right? The old eyeball method, which could be okay for some people, but not really quantitatively good. You could compare it to something nearby, like pi thirds is like 1 point something. And so it should be somewhere in the neighborhood of square root of 3/2. You could do Euler's method, remember. And that uses the power of the simplicity of the line, but it breaks it up into several steps instead of one big step. And then, of course, we learned in 9.2 that we could use a Taylor polynomial that wasn't linear, quadratic, cubic, higher degree. And as we add more terms in the polynomial for the approximation, the better the approximation is, and the further we can venture out on either side of the center where we're creating that polynomial. And so we've already talked about error bound a couple of times this year. We talked about the integral test. Remember, the integral test says if you find the partial sum of the first, let's say, 4 terms, you could then determine how close that is to the actual sum. That is, you can get you could bound the error, okay, as to how far it is from the actual. We also talked about the alternating series remainder, which is also another name for error bound. But the alternating series only works if the terms alternate. This one works all the time. So here's kind of an important idea. Let's say we have a function, and we can represent it by a polynomial approximation. If I then add what's left over, I get an equal sign here. Our actual function is the approximation plus the remainder. The remainder is what's left over from our approximation to the actual. And I think you could see that. Let's say we have a function over here. Let's just make up some function, call it f of x. And let's say we're going to center it right here at x equals c. I can fit a polynomial to that function. It might look something like this, and then it might look something like that. Okay? So remember that at the center, the polynomial function, which I'll call this p of x for polynomial, that's going to be our either Taylor or Maclaurin. In this case, it would have to be Taylor. That would be our polynomial that approximates f of x, and they are exactly the same at the center. But if I go left and right, now we just have an approximation. So the actual error is going to be this right here. It's going to be, let's say I want to evaluate it over here at some other x value. The difference between the actual and the approximation is the actual error. But we're not going to be able to find the actual error. Because if we knew how to find the actual error, we wouldn't have to be approximating at all, would we? We could get the approximation, add to that the actual error, and we can get the actual value. And that just doesn't work. So what our hopes are then is, can I at least bound the remainder? Can I bound the error so that I know that I'm at least within some reasonable margin of what the actual is? Okay? And that's what Taylor's remainder theorem or Lagrange error bound, interchangeable names, essentially does. So if you basically take this equation and you solve it for the remainder, you get the actual function minus the approximation. And that's a pretty typical thing like in science. You get the observed minus the theoretical. And if you take the absolute value of it, because could be positive or negative, you get the error. So we're going to define the remainder function or the error function, they're kind of used interchangeably, to be the absolute value of t sub n of a. And what that is going to be the Taylor polynomial of nth degree evaluated at a. So up here, I could say the center is at c, and let's say we want to evaluate it at a. All right? So I want to know on this interval here, what is the maximum that error could be. Can't find the actual area, so what is its maximum? We can define an upper bound for the error to be this. And this should be less than or equal to, not equal to. Okay? The actual remainder, using an nth degree polynomial at a, is this, but we can say that it's going to be less than or equal to this. And that's what y'all saw walking in. And there is a derivation of this, which we won't go into, because you don't need to know the derivation. Maybe we'll talk about it after the AP exam. All you have to do is kind of memorize it. And I think I went a little bit happy with the absolute values there. These don't have to be there. Okay? So what we have is, let me rewrite it. The actual error, we can call it the error, or we can call it the remainder function at a. It's going to be less than or equal the absolute value of the n plus first derivative evaluated at some value z all over n plus 1 factorial, and the absolute value is only in the numerator, times a minus our center to the n plus first. Okay, so this is specifically, if I want to figure out, okay, I'm going to evaluate the Taylor polynomial at some value of a, then I know that my remainder, the bound on my error, is going to be less than or equal to this part right here, the n plus first derivative, over n plus 1 times the value I'm evaluating it at, a, minus the center to the n plus first. So this part right here should look relatively familiar to you, right? Because when we were generating Taylor polynomials or Taylor series, that kind of has the same feel to it, right? Remember, the coefficients of your nth term are going to be the nth derivative at the center divided by n factorial times x minus the center to the nth power. The only difference is this is n plus 1. So what this entire process hinges upon is, how do we find this? How do we find that value right there? Well, let's talk about this value. That value, if we could say that this right here, the n plus first derivative at some value of z, is, let's say, less than or equal to some maximum value. We'll call it m. On the interval. We're only interested in the interval from our center c to our approximated value a. So if we come back up here, we're only trying to bound the error on this relevant interval right here. C is our center, and a is the value we're approximating it at. Outside of there, we don't care. So if I could somehow find the maximum value of the n plus first derivative, then by the inequalities, I can say that this is less than or equal to m over n plus 1 factorial times a minus c to the n plus first. Okay, and I'll put absolute values around it. So what it comes down to for Taylor series error, or Taylor polynomial error, or Lagrange error bound as it's called, is essentially finding the maximum value, the absolute maximum value of the n plus first derivative on the open interval from the value you're centering it at to the value that you're finding. After that, it's really going to be just a plug and chug. Okay? So there's a little bit of theoretical background. It does look scary, but it's not. Okay? It's not. I'll show you why it's not. Let's work an example. Okay? By the way, here is my Microsoft Paint contribution to Joseph Louis Lagrange with a ZZ Top beard. Yeah. It almost looks like he was born that way because my skills are so mad. All right. Yeah, the white around it. Yeah. I think I had to go through there by hand with the little cutting tool, and I just got lazy. But anyway, that is Joseph Louis Lagrange. You might remember Lagrange without the beard from the mean value theorem. He's the guy that took Lowell's theorem, loosened up the restrictions, and came up with the broader MVT. So he's a pretty important guy. Let's look at example 1. Okay? It says calculator permitted. We'll see how far we can get without it. Let f be a function All right. Any objections there? So far, so good? Let f be a function. All right, cool. Yeah, we're off to a good start. I'm fine. Let it be a function. Yeah, leave it there. Just stop right there. That has 5 derivatives. Sweet. That means it's differentiable at least 5 times on the closed interval from 2 to 3. Also assume that the absolute value of the 5th derivative is less than 0.3, sorry, for all x on that interval. So what does that mean? Yes, m is essentially equal to 0.3. 0.3 then is the maximum value that the 5th derivative takes on in the interval from 2 to 3. Okay, so that's important. In this case, they're handing it to you. And that a 4th degree Taylor polynomial, call it t sub 4 of x, centered at 2, is used to estimate the function at 3. So that's why it's important. Let's say we have x equals 2 right here, and we have some function f of x that looks like that. We are fitting a 4th degree Taylor polynomial, which, man, I can't even try to draw this, but let's say it looks something like that. This might be a 4th degree Taylor polynomial. At 2, it's going to be the same, but we're using the polynomial's value at 3 to approximate the function value, the actual function value at 3. And so the actual error is that right there. We don't know what the actual error is. So what we're trying to do is on this interval from 2 to 3, we're trying to find the maximum possible error that it takes on. So then we know that our 4th degree polynomial approximation of f of 3 is going to be within a certain tolerance, if you will, of the actual sum. All right. How accurate is the approximation? You have 4 decimals. Okay, so here's what it says. We can, let's go ahead and do this. If we call the purple function, let's call that t sub 4 of x. All right, so everyone okay with the idea of a Taylor polynomial? We're using a polynomial to approximate some function f. They're always the same at the center, and then after that, they kind of drift apart. So we just like we would with the tangent line, we want to see, okay, what is t sub 4 of 3? Right? Because that is going to approximate f of 3. So just like with linearization, right? We said f of something is approximated by L of something. We want to know how good is that approximation. So here's what we do. We know then that the remainder using a 4th degree polynomial, so we'll use r for the remainder function, using a 4th degree polynomial evaluated as 3 is going to be bounded by, which means it's going to be less than or equal to the absolute value of the n plus 1st derivative. So here's what's nice. It's pretty easy. If we're using a 4th degree Taylor polynomial, this ends up being our n. And if you remember in the formula, we're looking at the n plus 1st derivative. So if n is 4, what's n plus 1? 5. So we want to find the maximum value of the 5th derivative at z. Now let me talk about z here. Z doesn't really matter. We don't really need to find z, but z is going to be something between, in this case, our center, which is 2, and the value we're approximating it at 3. We don't care what the x value is where the maximum occurs. We just want the maximum value. Okay? So the error is going to be bounded by less than or equal to that divided by 5 factorial times. And just like we would with generating terms, instead of x minus c to the 5th power, what is our x value? Well, we're evaluating it at 3 minus what is our center? 2. So it's really the same idea. Okay, this number here of 5 is going to match up with that, which is going to match up with that, just like it does in the Taylor terms. The only difference is it's going to be 1 larger than the n or the degree of our polynomial. And then the only other difference really is instead of having x minus 2, we're plugging in an x equals 3. All right, so now if I can figure out what this is, if I can figure out what the maximum value is for the 5th derivative on the interval from 2 to 3, I can compute it. Right, so in this case, it's handed to you. It says that the 5th derivative is bounded by 0.3. That's the maximum value. So we know then that this is going to be less than or equal to 0.3 over 5 factorial times, what's 3 minus 2? 1 to the 5th. And so that ends up being 0.3 over 5 factorial. So now if we just type that into the calculator, and I won't go to the one on the screen, I'll just type it in. Y'all remember how to get the factorial button? You hit math, and then you click over to the left to probability, and it's 4. Yeah, math, probability, 4. I end up with this number being 0.0025. Okay, so notice I don't really know what the Taylor polynomial is, but I could generate it if they gave me the function f of x, and I could certainly then plug in a 3 for all the x's in that polynomial. What we're focusing on right now is whatever that value is, I know it's going to be within 0.0025 of the actual function value at 3. Will it be exactly this far away? No. But this is the maximum error. This is the Lagrange error bound. It's the boundary. So the error could be anything that's equal to this or smaller. The error could be 0.0001. We don't know. We just know it's within that. So it's kind of like in statistics, you have a margin of error. This is kind of like that margin of error. You would be able to then figure out an interval in which the sum lives. Okay, so this is a good kind of example to get our toe wet, because in this case, the maximum value is given to us. And that's really the hardest part about Lagrange error bound. So here would be a nice follow-up question. Suppose that the 4th degree polynomial evaluated at 3 was 1.763. Okay, that would be the approximation then of f of 3. So I know that f of 3 would be approximately equal to that. You might be like, hey, is that a good approximation or a bad approximation? Well, if the actual value someone was telling me was actually 12, I'm going to be like, dang, that's a bad approximation. Okay? But it should, in general, not be that bad. Because, again, we're centering it at 2, and we're only drifting 1 unit to the right, and we're using a 4th degree polynomial. So it should be pretty good. But the question is, how good is it? How close is it to the actual? Well, it says to use your answer from part A to find an interval in which f of 3 actually must live. So let's do that. Because it could be on either side, it could be above or below, we're finding a maximum error bound. Here's how you figure out the interval in which the f of 3 could live. We're taking the absolute value, so it could be above or below. So all you have to do to figure out the interval in which f of 3 could live is take your approximation value, which is 1.763, and to get your upper bound, you're going to add the error bound, 0.0025, and to get your lower bound, guess what you're going to do? You're going to subtract it, 1.763 minus 0.0025. And so if you want to do the calculations on your calculator, that's fine. I'm going to just do them for you. I'm going to store that error as A. And so my upper bound, 1.763, if I say plus A, that gives us, and this would be a calculator question. They wouldn't really expect you to do these tedious calculations without, although it wouldn't be impossible. So that would be a safe upper bound. And then if you subtract it, subtract the error bound that you found, kind of like what we did with the alternating series, very similar to the alternating series, you get that. So it kind of gives you a margin of error. The actual function value, we know then, according to Lagrange's error bound or Taylor's remainder theorem, the actual value of f has to live between 1.7605 and 1.7655. Now, what could you do if, like, you had someone that was your boss or your wife, and she just wasn't satisfied with that? It's like, I need a smaller margin of error. How could you make that interval shrink? Use more terms. Exactly. You can use more terms, because remember the idea on the polynomials, the more terms you use, the better the curve wraps around the function it's representing, so the error gets smaller. So you could do that. You could also maybe, if you want to use the 4th degree, you could also consider changing your center of approximation. But is there anything that's more convenient to 3 that's 2? Maybe a 4? That's still about 1 unit away. So you could do that. But yeah, in general, you're going to add more terms. So I think in statistics, they have a confidence interval, right? You have a margin of error, and then you have a confidence interval. I'm 98% sure that the real value lives in this interval. This is a 100% confidence interval. This is really nice. We are at 100% confident, 100% sure that the actual value lives in that interval. Okay? So it's pretty good to have a sure thing. So then the follow-up question, as I look at my watch that doesn't exist, could the function value equal 1.768? No. And it says, why or why not? No, comma, since, 1.768 is not in the interval, the definite article, from what? From part what? From part B. And that's how you'll answer it. These actually could be real free response questions. You find the interval in B, and now you can refer back to the interval in B. Yeah, it's not. Part D, could f of 3 equal 1.761? Yes. Yes. Why? Since 1.761 is in the interval from the aforementioned part B, because we've already mentioned it once. No, you don't have to say that. Just from part B. Okay. Any questions on that? You have the conceptual idea of what an error bound is and how it's useful. The formula can get a little bit daunting, but don't let it daunt you. If we work enough examples, you'll have the mechanics down. And that's really what you're going to be responsible for. Our lunch is at 12:30, so we have a couple minutes. All right, so this one was easy. They handed you the maximum value on the interval. Are they always going to do that? Maybe not. Important. Ooh, this is the first time I've seen this graphic all year long. Must be important. I didn't make this one, no. That's way beyond my skills. I think I just stole this one from Google Images. Yeah. But whoever did it did a fantastic job. You can't even see any outlining or anything there. Yeah. Okay. Sometimes the value blah, blah, blah of this, that's what the whole thing lies on the interval between our center C and the x value, which we would like to evaluate it, is itself not explicitly given. It was explicitly given to us in the previous problem. Sometimes it's not given, and sometimes it's not actually easy to find. So in this case, what we're going to do, since we're trying to choose a safe upper bound, we have to choose the first known reasonable rational number that's greater than that outside the interval. Now the key here is you don't want to choose something that's too big. You don't just want to just say, the maximum value of the error is like 1 million. That's very useless, isn't it? So then, if you just said that, then up here the sum could be between 1.763 plus a million and 1.763 minus a million. I'm just going to go to a million just to be safe. Well, you got a huge margin of error. That's no good. So you want it to be as small as possible, but you also want to keep 100% certain or confident that it's actually correct. All right? So if you can't find the maximum value on the closed interval between your center and your x value, you're going to venture out of that and find the first safest reasonable maximum value for the function. Okay? I will show you what I mean after lunch. I think that's enough to digest for an appetizer. Okay? Yeah, have a fantastic lunch.